So last time we discussed how HSG implies hardness. So if you have an HSG, then look at the annihilator. The annihilator polynomial will be explicit and it will be hard for that family of circuits for which you had HSG. So in particular, if you solve black box PIT for circuits, then you get these three properties. So you get a multilinear E-computable polynomial QM that is 2 raised to m hard. Okay, so this constructing this QM currently is an open question. So it's open to whether QM exists. So existence of this family of QM is not known, and this is implied by black box PIT. Now we ask the converse question, which is if there is hardness, if there is such a QM, does it give black box PIT? Okay, so we will now show that. Any questions till now? Okay, so our theorem is due to Carbonet-Impagliazzo and then a version by Agarwal-Vinay. So we'll assume that there is a QM. So let QM be a multilinear polynomial family. E-computable, which is condition number 2 above, that is not computable by sub-exponential sized circuits. Okay, so this polynomial is hard. You cannot compute it even by, you cannot compute it. Basically, sub-exponential in m here means 2 raised to small o of m. To be precise, so it will require 2 raised to big omega m. You cannot do it in 2 raised to m to the epsilon, for example. There is no algebraic circuit of that size. But when you look at the coefficients and the bits there, they are computable in 2 raised to m. And the circuit size is also expected. We are assuming the circuit size also that is required is 2 raised to m. So then so what we will show, or what the theorem concludes, is that there is a efficient map that will take a circuit with n variables and reduce the n variables to log s variables without changing the non-zeroness of the circuit. So there is a variable reduction or a dimension reduction. Okay, so that is what the theorem says. Then there exists an efficient variable reduction for VP circuits. Reducing n to log n, big O of log n variables preserving non-zeroness. Right, so up to PIT, this is a very useful polynomial time variable reduction, because it will reduce the number of variables from n to log n. So how is this related to PIT? If you have a circuit where the size is s and the number of variables is log s, how fast can you solve PIT deterministically? In this polynomial, the number of monomials will be s to the log s. So you expect, just by opening up the circuit, you expect it to be doable in s to the log s time, right, which is quasi polynomial time algorithm. So this basically implies a quasi polynomial time black box PIT, but this is much stronger. It's a much stronger statement because it's actually giving you a variable reduction. Is the statement clear? Okay, so we'll prove this. It implies an s to the log s time black box PIT algorithm, which also means hitting set generator. Size of the hitting set and the time in which it will be computable is s to the log s. Right, which is nearly solves black box PIT, but still it is not polynomial time.
It's more of a structural result than.
Not clear. I mean, it doesn't tell you anything about the structure of the circuit. The circuit is still black box. It seems to be only a PIT result, because this variable reduction, what is it preserving? It is preserving only one thing, that is non-zeroness. So it's only a PIT. The application seems to be only PIT. I don't see any other application. Right. So assume this QM exists. This family QM. Assume QM as in the hypothesis. And suppose somebody gives you a circuit C. Of size s, computing a polynomial of degree less than equal to s. This we can always assume because we are only looking at circuits kind of in VP. So whatever is the size, we can assume is also the number of variables, and we can assume it is also the degree, because everything is polynomially related. So we can just take an upper bound s. So now using QM, how do you reduce the number of variables in C? Right, that is what we want to do. So how do we reduce its variables to order log s? So it has potentially it has s variables, and how do you reduce it to log s? So this by itself is a completely non-trivial question. I mean, why should there be a map that is efficient and reduces the number of variables? But there is an interesting way to use QM for this. So we'll use QM for very small m. Very small means around log s. So it is log s variate. So for s variate circuit C, we will actually use around log s variate QM. M is equal to log s. And but QM is just one polynomial, right? So I mean, we can feed QM in C, but that is only, we are just feeding it in x1. what do you do with x2, x3 and xs? How do you feed qm in the second variable x2, for example? If you keep changing the arguments in qm, then you keep increasing a variable, and so then there is no variable reduction, right? So you have to start with a small set of variables, log s variables, and compute qm, for example, at different subsets of this, right? So that is the only thing you can do at this point. So we'll use qm to feed into C. For different arguments chosen from a small set of variables. So how do you design these subsets? Say the number of variables you have fixed is 100 times log s, and then you want to evaluate qm on various subsets, each of size say log s. So how many subsets are there of size log s of a superset 100 log s? Definitely more than s, right? So you will get enough subsets, so you will get enough evaluations of qm, which you can then just feed into x1, x2 dot xs respectively. So the question is, what are these subsets? What are the good subsets? Well, you can say take all the subsets, but then the problem is ultimately you have to prove that C will not vanish at these values, at these evaluation point. So we have to do this carefully. So what we will try to simulate is nearly disjoint subsets. So suppose in the ideal case, if all the subsets were disjoint and you evaluate Q on these disjoint subsets, then is it easy to see that C at this will not vanish, right? But then that we cannot afford, because there are so many variables in C, so we cannot afford so many disjoint subsets. Yeah, because you are evaluating QM at disjoint subsets, so it is like one is x1, the other is x2, the other is x3. There is no overlap.
The original circuit also had separate variables.
And it was non-zero.
Right.
So when you evaluate it at algebraically independent things, it will remain non-zero, because x1 to xs is exactly that. They are only special because they are algebraically independent. So if you take, so maybe this idea is worthy of being written down. So idea is evaluate QM at S1, S2 and let's say Sn, where these SIs are subsets of variables x1, let's not take x1, x2 dot x big O of log s. So from this base set of variables we will pick subsets. Let me be precise with the notation. So this will be x bar S1, x bar S2, x bar Sn. Si is a subset of 1, 2 dot log s. Okay, so yeah, these subsets are not too large, because the universe is only log s big, but they are many. So these subsets are n many. N is, you can think of n and s as the same. that will not hurt. And m is also some multiple of log s. Okay, so qm has m many, qm is m variate, and the size of S1 is also m. So size of Si is m. So it is well defined, these evaluations are well defined, qm x S1, then qm s x bar Si. Now if S1 to Sn were all disjoint, then C will not evaluate to 0 at this. Right, so we want to basically achieve this, that C at these values of qm should remain non-zero. That is what we want to achieve. This is definitely true when S1 to Sn are disjoint, because then the variables you are using are really different, algebraically independent. So evaluations of qm are also independent, and so C will remain non-zero. Is that clear? But we cannot afford that, because that will be too many variables. We cannot achieve that with log s, with base being that. So what we will try to achieve is nearly disjoint. Okay. So yeah, this is the rough idea, but implementation will be complicated. Okay, so first we will define what is the meaning of nearly. I mean, nearly cannot mean truly disjoint, because you need so many subsets from a small base set, so obviously they will overlap. So how much of so can you really minimize the overlap, and to what extent? Right, first we will define that. Second part would be to actually showing that although there is an overlap, the circuit doesn't vanish at these QMs, and that will need some algebraic results. So let us try to go through the details. Any questions about the idea? Okay, so let's say C has n variables z1 to zn. These are the n variables, it's n variate. Let I be the family of subsets S1 to Sn. What we want in combinatorics, it is called Nissan-Wigderson design. So C log n, D log n, 10 log n, Nissan-Wigderson design. So some people have heard about this, because this is also used in Boolean complexity, which we see in CS640. So let me define it. Basically, before definition, I should say that this the first parameter here refers to the size of the base set. So there are C log n variables overall. D log n refers to what is the size of the subset you want. So that's the base or universe. This is the size of subset. So obviously D is less than C. These are absolute constants. And finally 10 log n refers to the intersection size. Okay, so 10 log n bounds the overlap. So we want a lot of, as much as possible, as many as possible d log n sized subsets of a c log n universe with intersection bounded by 10 log. Okay, this is what a design is. So yeah, let's now formally write the definition. So let L greater than n greater than d be numbers, natural numbers. Collection I of subsets I1 to Im, where m is something else, some other parameter. So a collection I of n size subsets of the universe 1 to L is called LND design if ij intersection ik size is upper bounded by d less than equal to d for all j k different. Okay, so an LND design is just a family of subsets of a universe 1 of the universe 1 to L, such that the subsets, all of them have equal size n and intersection is bounded by d. Yeah, so when you look at this general object LND design, what would you think of L if d was 0? If you wanted d to be 0, which means disjoint subsets, L has to be, well, L has to be nm. You cannot work with L smaller than nm, right, if d was 0. And similar arguments you can make if d is a constant. So if you want the intersection to be very small, then your L will blow up, and we don't want that because our m is actually large. In the application, our n, if you see, m if you see is exponentially bigger than LND. So we actually want L to be exponentially smaller than m, something like log m. So for that we have to actually increase d also to log m, and then there is a theorem that such designs exist. If L and D are comparable, then designs exist. Okay, so that has many proofs. We'll skip all of them. So you can see that in some other place. So let me just state the lemma. It's by Nissan Wigderson 94. So in fact, it's there is a constructive proof. There exists an algorithm that on input L and D, assuming obviously L greater than n greater than D, but also L sufficiently large, so L greater than 10 n square by D. So if this 3 tuple is given to you, the algorithm will output a design. Design I having a lot of subsets. So having m greater than equal to 2 to the d by 10, so exponential in d subsets in time which will be quite reasonable. It will just be 2 raised to L, that which is the number of subsets of your base set or the universe set. So essentially in the algorithm you are allowed to go over all the subsets of your universe and out of these subsets it will actually identify m subsets which are LND design, right, and these subsets are of size n, all of them. So can you guess the algorithm?
Probably some sort of, you probably construct some vector space and then take a particular subspace.
Yeah, so if you think algebraically you will do that, but here you can also just use a greedy algorithm. So you just start with an n size subset and then try to grow this as much as you can, and there is a probabilistic argument saying that your greedy algorithm will continue to grow till you reach m many subsets. It will not stop.
So that's not very explicit, right?
It's an explicit algorithm.
You can't.
It's completely explicit. You can go home and implement in C.
Sure, but
If you want structural details, that they are absent. Yeah, it doesn't tell you any structure or how is this working.
it would be hard to index your family and so on.
Exactly. So a greedy algorithm or approach works. So it's an interesting exercise.
There are like algebraic constructions, right?
And there are algebraic constructions, yes. Yeah, there are beautiful algebraic constructions which have in some sense better parameters. Yeah, but what this greedy approach will give you will also be optimal in a way. And yeah, I can mention there is also a polynomial based construction. Over finite fields. Yeah, so there are at least 2 proofs, maybe more, which will give you such designs. So any question about what happened here? So the remaining details I skip because this is really a combinatorial thing. It's a detour on what we are doing. Okay, so now going back to our hard polynomial QM. So for that we need this design where the subsets are nearly disjoint and many, and using a very small base set. Let I, so we continue where we left before. So let S1 to Sn, okay, now our M becomes N, I think. Yeah, so there is some confusion between the lemma and the application, but S1 to Sn, so we want n subsets, which is a C log n, D log n, 10 log n design, Nissan-Wigderson design. For constants, suitable constants, C greater than D greater than 10, and you also wanted that property, right, this L greater than 10n square by D. So what does that give you? C greater than 10D square by 10 . Yeah, so which is satisfied trivially, so that isn't a condition, extra condition. So just pick constant C greater than D greater than 10 and apply the above lemma, and there is a design. So by the lemma, I can be constructed in how much time? 2 raised to log n, right? So poly n time. So the construction is free. Right? You had n variables or size S circuit. For that, in poly S time, you can construct the design. There is an algorithm, and you were already given by someone QM. So just evaluate QM on the design and claim that this is the map, variable reduction map. Right. So the construction is over. So now we map Z1 to Zn variables to very few variables, x1 to xc log n. Let's call this x bar as, so Zi will be mapped to, so this variable reduction map is, I will call it phi. So where does Zi go to? Directly, so evaluate q d log n at x bar, and the subset you will pick is Si. So this is for all I 1 to n. Is this clear? So Si is of size d log n, right? So this x bar Si is actually a d log n tuple. So you can happily evaluate q sub d log n at this tuple and feed this into Zi and do this for all the variables Z1 to Zn. Right. So this is reducing n variables to exponentially few variables, just x1 dot xc log n. C is a constant. So now the surprising claim. So even after reducing the variables exponentially fewer, we are claiming that the things in C cannot cancel out. So C at phi Z bar is non-zero. Okay, that is the claim. So let me introduce some notation. So let's call this Pi, and then this is C P1, P2, Pn polynomials. So when we evaluate C at these n polynomials, log n variate, we don't get 0. Do you see a proof of this? So what happens if this is 0?
Probably you want to sort of show that P is not hard, right? Because you have not used that fact anywhere yet.
Exactly. So you will, the only thing you can contradict with is that Q is hard. So you have to basically deduce from the zeroness of the circuit that Q was easy. So how is that possible? Right, that's a really new phenomena.
Right.
Sorry?
Just substituting variables one at a time.
Yeah, so let us do that. So suppose not. So suppose C at P1 Pn vanishes. So then since C Z bar was non-zero, and when you substitute P1 to Pn it vanishes, we deduce that there is a J such that C P1 to Pj just fix the first j places. That vanishes, but if you fix one less, it doesn't vanish. Right, this is obvious. Well, because you know that if you don't fix anything, then it is non-zero. So you will, from the left, you will start fixing the variables, and at some point non-zero will become 0. So that is the point j. J minus 1 to j transition is the place where non-zero is becoming 0. So this tells you what? If in a polynomial you substitute something and it vanishes, then it means you have found a root, right? So this means that Zj minus Pj is a linear factor of this guy, which is non-zero. Right, so there is this non-zero polynomial whose root we have identified as Pj. Now C is a small circuit, right, and Pj is a root of that. So what does it mean? Pj by itself is also a polynomial. It's a polynomial root of a small circuit. So intuitively Pj should also have a small circuit. And if Pj has a small circuit, then Qm also has a small circuit, which contradicts our cardinal assumption that Qm is exponentially hard. Right? That is the line of argument. But you have to look at the parameters. So let's actually check that. Yeah, so we have to just wondering how to motivate why a lot of calculation would be necessary. Why is this? What I just said is not a proof. So one thing is that you have to compare exactly what is the bound on circuit size of Pj that you are getting, and because for Qm, what did you assume?
You assume it's exponentially hard, but then you're using like a log size.
The assumption long time back was this, that for Qm there is no 2 raised to small o of m circuit. Now m we have taken to be d log n, d is a constant. So this is n to the small o of 1, right? So to get a contradiction, we have to actually show that this root that we got identified, the root has a circuit of size n to the small o of 1. So say n to the 0.9. No, not 0.9. Yeah, I mean it should be a
1 minus epsilon.
small function. Small o of 1, right? So I cannot put a constant there. So something like maybe n to the 1 over log n. It's a function that tends to 0 in the exponent. So you have to show that show that strong upper bound on the root, but that is not possible because see, already your circuit C, it is small, but it is not that small. It is not n to the inverse polynomial, right? It is only polynomial sized. It has size s, and you have plugged in these Pj's, so it has an even bigger size. So from that you cannot really hope to deduce that Pj has a very small size. So yeah, we have to work on this. This is not done. Yeah, let me just go through this. C we assumed has size. Size s, yeah, and m we have taken to be log s, so it's s versus log s. So n and s you can assume to be the same thing, and m is log s. So your Nissan-Wigderson design was for parameters around log s. So maybe we write it down. So this is size s, and these pj's are around log s variate. And the question we are asking that for pj, is the size smaller than s to the small o of 1? That is the question. Yeah, so let us now do some tricks here and there to get to some sort of a contradiction. So we will actually not get this, we will not get s to the small o of 1, but we will still be able to contradict the hardness of QM. Right. So that is why we will do a lot more calculations. Okay. So what we will do is first we will fix the variables. So let us fix zj plus 1 to zn. And variables xi's that do not occur in Pj. So remember, Pj is x bar Sj, it is given by this Sj subset. So since we are only interested in the complexity of Pj, let us fix all the other variables. So all the other x's and all the z's which you are seeing here, except zj, right? So because they are really unnecessary and a disturbance, so we fix them to random values from the base field. So I mean, if you fix the variables, extra variables to random values, then your circuit non-zeroness and divisibility conditions won't change, right? I mean, a non-zero circuit cannot vanish at a random fixing. This is again a consequence of Schwartz-Zippel lemma, and obviously when you do this, the divisibility condition will not get violated, right? So we are really not changing anything, we are just making our life simpler by removing the extra variables. So where do we get at? So this reduces us to the case Zj minus Pj is unchanged, and it is still a factor of some circuit C prime with P1 prime. Okay, so P1 corresponds to the subset S1. Now in x bar S1, you might have fixed some of the variables, right? And which are these? These are the ones other than Sj. So when you fix them, what remains? Only the variables which are in Sj, they remain. So P1 prime has arguments x bar S1 intersection Sj, then P2 prime S2 intersection Sj, dot dot P j minus 1 prime and Zj survives, and this is still non-zero, right? So we have this. So basically on the RHS, these Pi primes which we have, their variable set is the intersection. with Sj. And what do you know about the intersection? It is only 10 log n, right? Yes, actually there was another point why we did this variable restriction. If you look at this identity here, we don't have a good bound for P1 and P2 because these are coming from a hard polynomial, right? So the bound for this is actually bad. So that is another reason why we do not get immediately something for Pj. But now once you have restricted some of the variables, you see that now the variables are only S1 intersection Sj, which is very small. So now P1 prime is a polynomial on very few variables. Instead of original d log n, it's now only 10 log n, right? So there is a shrinkage in the variable set. So what is the trivial size bound you get for P1 prime? So note that Sk intersection Sj is less than equal to 10 log n for k less than equal to j. So this means that P1 prime at whatever variables it has size, in fact, less than number of its monomials. And what is the number of monomials? Yeah, it's a we started with a multilinear QM. So this is just 2 raised to 10 log s, 10 log n. Yeah, so let's continue with this notation. So this is n to the 10. So the overlap size basically gives you a complexity upper bound on these pi primes, the trivial one, just counting number of monomials that it has. So that is n to the 10. So now for the whole thing, the C prime with these hard polynomials now restricted being fed in, overall size is what? Yeah, so for this now the overall size is the size of S, which was C, which was S, plus another n, so n to the 11, right? Certainly not more than that. That is the overall size of this RHS. Okay. If we had done the same calculation before, then we would have gotten d in the exponent instead of 11. So that I don't want. Now we have s plus n to the 11, and there is a very fundamental result saying that for small circuits the factors are also small circuits. Okay, so this we do in another course, CS 681. So that is a it also has an explicit algorithmic version as well. This is the computational number theory in algebra. Kaltofen. So this is, so we do the strongest version of this, which is an algorithm, an explicit algorithm for finding these factors.
Does that imply?
That is harder.
Does that imply a circuit?
Well, the circuit size or circuit complexity proof is much easier. That algorithm is more complicated.
The black box.
Yeah, so a non-constructive proof is easier. It's implied by whatever tools we developed. Much simpler. So that again we cannot afford to go into that. So let us just state it. So Kaltofen 1989. So this result is factors of small VP circuits are also small VP circuits. Okay, so in words it says that, and quantitatively says that if you have a size S, degree S circuit and you look at a factor, then the factor also has size S cube, around S cube, and degree obviously at most S. Okay, so there is a size blow up of only cube, not much more than that, which is highly non-trivial. I mean, the connection between circuit and its factors, it's not immediately clear that there should be a connection in the size complexity, because we are talking about multivariate circuits. So multivariate circuits have exponentially many monomials. So factors also have exponentially many monomials. But why should there be a small circuit computing this? Right? This is a highly non-trivial fact, but it's true. And there is an algorithm also. Okay, so and there is also an algorithmic version of it. It has a algorithmic version as well, that is black box. So which is why it is even more fundamental, because it not only shows the existence, but it even when you are given a black box circuit, then Kaltofen's algorithm will output all the black boxes for the respective factors. Okay, which is an amazing thing. So it works completely at the level of black boxes. Okay, so when you apply this, what you will get is that Pj has a circuit of size, this is S plus n to the 11 was the circuit size which it was, of which it is a root, or Zj minus Pj is a factor of that circuit. And so by Kaltofen there is a absolute constant E, so S plus n to the 11 to the E, which bounds the size of Pj. So where E has nothing to do with independent of C and D, right? E is just this constant which appears and it's around 3. So the exponent is around 3. Okay, and C and D we haven't even fixed in the Nissan-Wigderson design. So let us now, so S and N were comparable, right? Okay, so let me then just let me just simplify it. Let me remove n to the 11 from here. Just we can replace it by S. So S plus n to the 11 is some polynomial in S, and we just absorb it in E. Okay, so I say that Pj has a circuit of size S to the E, where E is an absolute constant totally independent of C and D. So for example, E may be 33 or 35, whatever, it's some fixed constant. C and D are unfixed right now, yet to be fixed. So since Pj, which we started with, is q sub d log n x bar Sj, has complexity. What is the complexity that we assumed?
S to the small
has complexity 2 raised to omega d log n. Right, we assume 2 raised to omega m, and m in this case is d log n. So Pj has complexity 2 raised to big omega log n, and d is still unfixed, so we can keep using d log n as a variable. So now look at these two things. Look at this and look at this these two expressions. So let me make it s to the big omega 1, big omega d. Right. So one side you are saying that Pj has complexity s to the e. On the other side you are saying that Pj has complexity more than s to the d, with omega hiding some absolute constants, but it definitely suggests that you can pick d to be much bigger than e to get a contradiction, right? So that is the source of a contradiction, that this e that you get from Kaltofen and this omega d that you get from your premise, they will contradict because d is free. So you pick d suitably and then use that Nissan-Wigderson design. That's the proof. So we pick omega d to be sufficiently bigger than e. So this exponent which is sitting depending on d, we pick it big enough to get a contradiction. So what does the contradiction mean? That it could not be a factor, so which means that it cannot be 0. Right, so that's the proof of the claim, which is assuming some fundamental things. So I have left Nissan-Wigderson design construction as an exercise, and also the whole area of black box factoring as an exercise. So that is a plug for the next courses.
But for this specific case, we don't need algorithmic, right?
Yeah.
Existential would work.
Sure. But existential is easier, it doesn't mean it's trivial.
Definitely. Yeah. You don't have to look Kaltofen's paper for that now.
Well, you have to look at Newton iteration.
Yes.
Okay. So, and what is the consequence of this? So, the consequence of all this for PIT is that you have in deterministic polynomial time, you have reduced the variables from s to log s. So C p bar is non-zero and it has C log n variables. And the degree is what is the degree? So initially if you assume the degree to be s,
D log n variable.
no, d is the smaller one. The base set is C log n. Yeah, so that is a good point.
Oh, right,
It
okay.
seems that we are working with d log n, but the base set is bigger. That is the range where you are mapping. And the degree originally of C was S, but when you plug in P, you may grow it slightly because P1 has degree around log S or log n. So degree is not too big, S log n. That's one consequence. The second consequence is which follows from this. So how many monomials are there? well, degree s polynomial on log n variables, right? So it is s to the log n. Yeah, maybe in the notes I should merge n and s. It's unnecessarily hanging around. There was no need for this. So you get s to the log s monomials, and we have not done it. Maybe we can do it in the next class as a final, as an example of a PIT algorithm, that if your number of monomials is small, then you can do black box PIT. So this actually implies s to the log s time, or let's say HSG. For algebraic circuits. If, obviously, if QM exists. Not just hard QM, but with all those conditions that it should be explicit, E explicit, and multilinear. So hence, if there is hardness, then there is HSG. Okay, highly non-trivial HSG. So this in this implication, we are actually using the HSG for sparse polynomials, or sigma pi polynomials. Yeah, so I'll show you at some point what is this HSG design for depth 2. So it's just a sum of monomials. So if somebody gives you a sum of monomials in black box, there is a hitting set design for that, which is polynomial time. Actually, here you can do better. There is a very simple hitting set because the even the number of variables is so small. So actually, what you can do is if you take the degree to be d or delta, just pick delta plus 1 many field elements and take Cartesian product into number of variables. That is a hitting set. So if you call this degree delta, and if you call the number of variables n prime, then hitting set is something like 0 dot dot delta raised to n prime. That's a simple observation. So just delta plus 1 many field elements and try out all these possibilities for all the variables. Right, so this is delta to the n prime sized HSG. So here it's actually even easier. You don't need to invoke sparse PIT, but that also is true. That will need more work. Any questions? Fine. So then so then we will do a similar calculation for depth 4 PIT. We will show that if you can design HSG for depth 4, then you can design the same HSG for general circuits. So we will do that result, and we will maybe, if we have time, we will do this sparse polynomial HSG. Okay.